Good morning, ladies and gentlemen. Welcome to the technical presentations by newly elected fellows and foreign fellows, which shall be carried out in parallel sessions. In the first group, 2 sub-parallel sessions featuring presentations shall be made by fellows elected in engineering sections, namely civil engineering, mechanical engineering, chemical engineering, aerospace engineering, and mining, metallurgical, and materials engineering. In the second group, 2 parallel sessions shall be featured for fellows elected in engineering sections, namely computer engineering and information technology, electrical engineering, electronics and communication engineering, energy engineering, interdisciplinary engineering and special engineering fields and leaderships in academia, R&D, and industry. The lectures shall cover their most significant scientific and engineering contributions and highlight the motivation, novelty, and significance of their work that have been recognized by their election to fellowship of the Academy. I'm sure that you will enjoy the presentations, and it shall be my delight to introduce the fellows and invite them to deliver the lectures. Starting with 2 parallel subsections, namely Engineering Section 9, Energy Engineering, Engineering Section 10, Interdisciplinary and Special Engineering Fields and Leadership in Academia, R&D, and Industry. So we'll first start with Engineering Section 9, Energy Engineering. I invite Dr. B.K. Nashine, Outstanding Scientist and Director, Indira Gandhi Center for Atomic Research, Kalapakkam.
Everybody, good morning. I'm going to present development of electromagnetic devices and components for sodium-cooled fast reactor. Sodium-cooled fast reactor comes in a second stage of Department of Atomic Energy's program, where the schematic is shown to you, and the coolant used in this reactor is the sodium. You can see that sodium, the fuel is kept in the pool where sodium is there, and that works as a primary coolant, and there is a secondary coolant, which is also a sodium, and that takes heat from primary and transfers to tertiary, where water is converted into steam, and then finally it runs the turbine and which generates the electricity. So sodium plays very important role in a fast reactor program, and to have this fast reactor program successful, we have to carry out various tests in a sodium loop. The characteristic of sodium is that it is a very good coolant. It has got very good heat transfer capability. And at the same time, sodium is chemically very reactive. And the operation of the sodium loop and the reactor is around 600 degrees centigrade. So any component going to the reactor has to be tested thoroughly before going into reactor. Hence, this requirement of the sodium loop comes. Apart from that, there are various components which are conventionally used in other engineering systems but cannot be used in a sodium system. So it has to be also designed for the to make it compatible with sodium. Example is that different type of mechanical pumps as well as electromagnetic pump. Now, what topic I have chosen is, or my field of work is the electromagnetic pump. Now I am switching over to that. And this is the basic characteristic of electromagnetic pump. It doesn't have any moving part. And that helps this pump to be made very hermetically sealed, and leakage of sodium is avoided. This is the picture of one of the DC conduction pump. Basically, it works on an electrical principle that when a conductor is placed in a magnetic field, the conductor experiences electromotive force, and this force only pumps the sodium. So all this condition is designed and generated in this DC conduction pump, which is shown in this picture. and this works at the voltage of 2 volt and in the range of 2000 amperes, and it can be dipped in a sodium of around 500 degrees centigrade. Next type of pump is of a similar class, but it is an induction type pump. We call it annular linear induction pump. The construction of annular linear induction pump is depicted here. Here we have a stainless steel pipe in which annulus is created by inner core, and in the annular gap there is a sodium. Outside of this stainless steel pipe is a magnetic core where three-phase winding is also wound. So when three-phase power supply is applied, there is a production of a linear moving magnetic field. This linear moving magnetic field produces current in the annular sodium, because sodium is a very good conductor of electricity, and this induced current in the sodium and the magnetic field produced by outside winding interacts with each other and produces the force in the sodium. This force causes the pumping in the sodium, and you can see that here there is a no moving part, which makes this sodium very much maintenance free. And the sodium is also in a very sealed boundary of stainless steel material or pipe. So this is again same principle what I indicated in previous slide. You can see that the magnetic field is radial and the current produced in the current is circular. So interaction of this radial magnetic field produced by outside winding and the interaction of current produced in the sodium causes a force F in mutually 90-degree direction, and this force pumps the sodium in the pipe, which is in annular gap. Now this is pictorial view of our design, and which was manufactured in Indian industry. You can see that white portion is the winding, and this teeth portion is a magnetic material that is outer core, and this is the inner duct which has got a annular gap between two pipes in which inner core is kept. So the sodium enters here. Of course, this duct will be kept in this cavity, and once this is kept there, it forms a full electromagnetic pump. And when we apply electricity in the three-phase electricity to the winding, the sodium gets pumped through this pump. So this is the inlet, and it goes outlet other side. This is the picture of the ALIP, which has been manufactured. This is wholly designed by us and manufactured in India. So we have indigenized this technology, and nowadays it is available in our country. And whatever reactors we are going to commission or we are installing in Kalpakkam, these type of pumps are used in all our auxiliary system. Different capacity of pumps have been designed and manufactured in India, and it is installed in a prototype fast reactor at Kalpakkam. Now, this is another variant of this annular linear induction pump, which can be submerged in sodium. Previously, whatever pictures I showed about annular linear induction pump, and that sodium goes inside and gets pumped and comes out of the pipe. But the requirement sometimes also comes that from a pool, we have to take out the sodium. So a requirement of submersible ALIP was also there, and this submersible ALIP has to withstand around 550-degree sodium. So a new pump was developed based on same principle. Only thing is, winding is a different type of winding. In previous ALIP, the winding is organic insulation, whereas here it is a mineral insulation. So this winding can withstand up to 600 degrees centigrade. We have designed it, we have manufactured from Indian industry, and we have field tested also. The picture which you are showing here is during manufacturing, you can see, and this is after manufacturing, and this picture is during the field testing, where this pump was submerged in a sodium of around 500 degrees centigrade and it has operated. And this graph indicates the characteristic of pump, which is flow versus head developed. So whatever is our requirement of pumping the sodium at submersible condition, we have achieved. And when situation demands that we have to evacuate sodium from any pools, this pump will be used. And already during testing, we have used it in a ICT testing, integrated cold trap testing. We have done it, and this was successful of our experiment. This pump can operate at 115 volt three-phase power supply, and its flow capacity is around 2 cubic meter per hour. This is one video which indicates that here I had put one rod, steel rod, mild steel rod, which comes out. But I think this video in this system is not working anyway, but that doesn't matter. And this, you can see that it is a mineral insulated cable which is used inside as a winding. It is totally hermetically sealed pump, and it can be submerged in a sodium, and this works at 550 degrees centigrade surrounding sodium, and it pumps out the sodium from the vessel. Next thing of my work is related to heater control panel. As I indicated that any sodium loop is an integral part of our R&D, and sodium being a solid at room temperature, it has to be heated up to 98 degrees centigrade, and as per the requirement of experimental condition, it has to be heated up to 550 degrees centigrade also. So we use electrical heating. For that, we have designed new type of heater control panel. Earlier, these heaters were heated by using a contactor, electrical contactors. Nowadays, we are using a solid state relay-based system. So this is a schematic of the heater control panel. You can see there is a solid state relay here. There's a fuse, which then this heater is connected to this panel, and there is a auto control of heater control. So, and this is the picture of heater control panel, which is being used in our sodium loop, because sodium loop has got trace heaters over the pipeline, and there are immersion heaters also in the sodium loop, which has to be heated to the required temperature. Now, another work which I have carried out during my span of previous few years is that, as I told you, that we have to put heaters, trace heaters on sodium pipelines. These heaters and thermocouples on the pipeline. Thermocouples are used to monitor the temperature, and heaters are used to heat the sodium through inside the stainless steel pipe. So those two components, heaters as well as thermocouples, have to be fixed on the pipeline over the length. So we use a shim of 0.7 mm steel. So that has to that is used for fixing the heater. So for fixing the heater, this seams is welded on the pipeline. So there is a need of a spot welding machine. This earlier, whatever spot welding machine we had was based on the contactor technology, whereas this machine is used based on the solid state relay, which has got a higher reliability, as well as it doesn't make any noise when we do the spot welding machine. So you can see here that there are two electrodes. One is for return path of the current, and the other is the where we want to spot weld. So this machine was also developed, and in all our new loops where our heater fixing and thermocouple fixings are required, this machine is used. So with this, I complete my presentation where I have depicted some of work which I have carried out recently. Thank you very much.
Thank you, Dr. Nashine. I now invite Mr. A.K. Balasubramanian, Director, Technical, Retired, Nuclear Power Corporation of India Limited, Anushakti Nagar.
Pressurized heavy water reactors form the major pillar of India's nuclear power program. The indigenous technology has matured and made a large number of strides in the development over the years. In my presentation today, I'll be talking about design, development, and engineering of Indian pressurized heavy water reactors, in which I was deeply involved. To start with, you are all familiar with the fission process, which generates energy as well as multiple number of neutrons. So it allows us to continue a nuclear chain reaction. So on the right-hand side of the slide, I have shown the steam power plant cycle. The boiler is replaced by the nuclear reactor, where a particular arrangement of the fissile material, that is uranium, and moderator and coolant with control devices is put. This slide shows the pressurized heavy water reactor, which is a pressure tube type reactor, which uses short length bundles of natural uranium. It requires on-power refueling. It uses heavy water moderator and coolant. Now, if you look at the saga of pressurized heavy water reactors, we can see in the initial phase of the program, it went through a good amount of indigenization, standardization, and then commercialization with a capacity of 220 megawatt power. At some point of time, it was thought that we can go for higher power, higher sized reactors to reap the benefits from economy of scale, which is we started with 540 megawatt, and then today we have the 700 megawatt PHWR, a reality. So I'll be focusing on these two reactors in the next few slides. When we go for a higher sized pressurized heavy water reactor, it calls for certain changes in the systems, primarily because larger core size entails, or due to larger core size, we need to have what is known as zonal power control, which controls the reactor in 14 zones. So a new system was developed. Similarly, the shutdown system was changed to direct injection of the neutron absorber into the moderator. This also required a large number of in-core SPNDs, self-powered neutron detectors, and so on. This was implemented successfully in Tarapur 3-4, and based on the feedback and the experience obtained, the next size of 700 megawatt PHWR was launched. Essentially, the core design was kept same, and changes were made in the coolant system and thermal hydraulics. Many improvements in the safety-related systems were introduced, which called for many first-of-a-kind systems and features. One additional point is design extension conditions, that is, beyond design basis scenarios, were addressed in the design and accident management program. This is one of the highlights of 700 megawatt. And based on this, the design and development analysis. Safety analysis was carried out to confirm safety under all postulated conditions and meeting safety goals and margins. So this is a state-of-the-art reactor. Now I'll be concentrating on the 3 C's as they are known, that is the power control, cooling, and containment. In the first part, the power control, as I mentioned earlier, the 14 zones are controlled by the zone control system. The information for the zonal flex stills is obtained through 3 pitch long SPNDs. Shutdown system 2, as was done in Tarapur 3-4, was used here, and so on. Now I move on to the core cooling. Here, generally the core cooling is ensured by forced circulation through pumps. And when in shutdown conditions, there is a dedicated shutdown cooling system. If the forced circulation is not available, thermosiphoning is used by keeping the elevation difference between the core and the steam generators as per the requirement. In case of a requirement, there is an emergency core cooling system, which is configured as 2 trains. This is again a new arrangement that is included in the 700 megawatt. Coming to the containment, the 3rd C, it's a double containment. Inner containment is lined with steel liners, which means in case of any radioactivity inside the containment, the leakage will be considerably less, thereby the dose outside will be significantly lower. Similarly, there is a containment spray system, which is again a first of a kind system introduced to reduce the pressure build up inside the containment, so that area under the curve can be reduced and consequently the leakage can be controlled. Various penetrations through the containment, they are all improved using special cable sealing arrangement. They are the electrical penetrations. Now, as I mentioned earlier, design extension conditions are addressed for each of these functions. Initially, for fuel and core cooling, there is a passive decay heat removal system, which is a first of a kind system, which helps in cooling the core in case of extended unavailability of power. Similarly, large number of hookup points are provided to send water to various systems for extended duration of cooling. The DG sets, dedicated air-cooled DGs are provided, and so on. With respect to the containment, one important provision is passive catalytic recombiner devices. As you know, in case of a very unlikely, very low probability event of core damage, then there is a likelihood of generation of hydrogen, which will come into the containment. So in order to reduce the concentration of hydrogen, passive catalytic recombiner devices are kept at various locations, which will ensure that the pressure in the containment does not go beyond a certain value. Now, one more provision has been made, that is containment filtered venting system. That is the ultimate barrier being the containment. Integrity of the containment has to be ensured. This is done using a filtered venting system, which can control the pressure inside the containment. So such provisions are built in, because of which the various postulated design extension conditions are addressed. I must mention here that in the original design of 700, all these were there, and after the Fukushima accident, these provisions were or are being backfitted in the earlier reactors of 220 and 540 megawatt reactors. Now, the most important aspect that is coming out is with containment, with such provisions, containment remaining intact, even for the worst postulated accident, There is no requirement of evacuating or relocating the public, staying beyond the mandatory exclusion area around the 700 megawatt nuclear power plant. This has been analyzed in great detail, and regulatory approval has been obtained for this. So this is one of the highlights of the 700 megawatt state-of-the-art design. All this was possible by basic designs and a large amount of qualification. First of a kind system qualification was carried out. For example, the left top picture is a hydrogen recombiner test facility. It's a world-class test facility in R&D center of NPCIL Tarapur. Similarly, there is a very elaborate thermal hydraulic loop for testing all these systems for validation. Lastly, a word on aging management. All the power stations, PHWR power stations, require very good aging management on various components. I'm here highlighting one such requirement pertaining to the coolant channel, that is called pressure tubes, where the fuel is located and coolant, high pressure, high temperature coolant is passing. By virtue of the high level of reactor, this material undergoes irradiation damage. So it is very important to monitor the health of this component, this tube, by a very elaborate in-service inspection, which is done at predetermined intervals during the life of the reactor. A detailed analysis for fitness for service is done. And in case of any particular issues, root cause analysis is done very elaborately. And every time it is ensured that the tubes are fit for service, and then clearance is given. And at some point of time, when it is really required to replace these tubes, provision has been made in the design to replace all these tubes, called en-masse coolant channel replacement. This provision allows safe and continued operation of the nuclear power plants. So with this, I end my presentation. Thank you very much.
Thank you, Mr. Balasubramaniam. Starting with Engineering Section 10, Interdisciplinary and Special Engineering Fields and Leadership in Academia, R&D and Industry. I invite Professor Giridhar Udupi Rao Kulkarni, President, Jawaharlal Nehru Center for Advanced Scientific Research, Bengaluru.
Thank you for the kind invitation to speak. I thought I would present part of our activities, just to give a flavor of activities going on in my group. And this project is related to smart windows. How we take, say, ordinary glass and bring in functionalities so that it can get integrated into a smart window. So I'll just try to present few results and also the background literature as well. Glass has been around us in kitchen utensils, making of windows on big buildings and spaceships and whatnot. Glass has been around for centuries now, and it has also seen some transformation, implementation of technology. We come across colored glasses because they are doped with certain oxides, which themselves are colored. At times they are doped with metal nanoparticles and they get specialty colors. Of late, glass is also covered with some laminating sheets to bring in additional properties like thermal insulation, making glass soundproof or even shatterproof, which is important during accidents. And of late, again with the advent of nanotechnology, several more technologies are emerging. For example, just one or two examples from the literature: making glass anti-fogging, by coating silicon nanoparticles mixed with polyvinyl alcohol is a composite. Similarly, by having a layer of Ag nanoparticles on top, glass becomes repelling. It starts repelling. It doesn't host bacterial species on top. It becomes antibacterial and also antiviral. Such results are around in the literature, and I'm not going to address today any of those. Rather, I shall focus on one sector, that is smart windows. Take ordinary glass and work with it such that you don't need curtains anymore. Glass can it control the ambient light passing through it at our will. So on-demand control of light passing through it. It is important because, as you see, when we have big glass panes covering windows and buildings, a lot of sunlight enters, and it's on the cost is on energy. One has to maintain air conditioning inside, and at will one should be able to control the bright light entry inside, and then one can save on energy. People talk about zero energy buildings, and in that context, functional glasses, smart windows are becoming extremely important. And there are many technologies. In the given example here, I'll be just covering it in brief, that one is able to switch the transparency of the glass, even for indoor applications. There are many technologies: thermochromic, suspended particle technology, microfluidics, polymer dispersed liquid crystal PDLC, and then electrochromic based transparent, what do you call this, smart panes or smart windows. I shall focus only on some 2-3 technologies given the limited time. This is microfluidic window, and so there are channels carved into the glass, say in between the glasses or sheets, through which a liquid is passed. And if the liquid is having a refractive index matching with the glass itself, then the presence of the liquid in the microfluidic channel is covered, is no longer seen because of the refractive index matching. It goes hidden, in which case one can see through the window, and it looks just like glass itself. This is the concept behind microfluidic window. And PDLC windows, on the other hand, work with liquid crystals. These are liquid crystal layers, and in that the small liquid crystalline domains remain randomly oriented. Only upon application of an electric field they get aligned, and in the aligned state, refractive index matching, and there are several other physics concepts here. But in the end, what happens is when the liquid crystals get aligned due to the electric field, light transmission takes place, and that's how they become transparent. So one can observe here that it is important to have glass enabling liquid electric field application, which means glass itself has to be conducting, and that's an important aspect. I'll come to that in a minute. Again, electrochromic smart windows, yet another technology many of us have come across. Sitting in the aeroplanes, you can see the passenger window pane, is user controllable. You can control the transparency just by applying the electric field using a toggle, and it can differentially get color. What's happening here is there are active layers in between glass panes, and these active layers are now doped with ions internally, and with increasing doping of ions, they get color. This is a solid state chemistry principle which is made into an application here. Again, one has to emphasize that each such window will have 2 glass panes which are optically transparent. They should be like glass only, and also electrically conducting, because you need to apply the electric field for the functioning of the window. And that's an important aspect related to the technology development of glass. So, what's the important aspect about it? The point is, none of these windows, what we talk, they are in practice actually, except in high-end applications like aeroplanes and all. The reason is, glass per se is not easily available as conducting. By its nature, it's a wide band gap insulator, and it doesn't conduct electricity at all. So one has to impart electric conducting nature onto the glass by some other means. And there are several technologies, and they're all rather expensive. One of the commonly used technologies is to coat it with indium tin oxide. Let's not forget, Indium is as expensive as silver is, but it is not recoverable at all, unlike silver. So you have smartphones, you have televisions, everywhere glass is made conducting by coating it with ITO. Now you can imagine the usage of ITO across the world. It's enormous, and actually indium is getting depleted. And issue related to recovery is a big problem because whatever gets used in a device is just trashed after the life of the device itself. There are many other disadvantages of ITO. Let's not get into that. And again, with the advent of nanotechnology, people are now looking for alternatives to ITO. How to bring in conducting nature to the glass pane using other alternate technologies. This slide talks about the fluctuation in the price of indium is, as you know, is sort of a semi-noble metal, and the glass used in smartphone is quite expensive, and that's why the phones themselves are expensive. Now, at CENS, that is Center for Nanoscience and Soft Matter, um, I was there for a while, for a few years, and now I'm back at JNC. And between the two institutions, we have developed technologies wherein we can impart conducting nature to a transparent glass without affecting its transparency. This particular project was done, part of it was done jointly with an industry in a vacuum, and I shall show you one or two results in this presentation. So here is a glass pane, and on the glass pane we are able to actually bring up fine mesh of a metal, given metal. It could be inexpensive metal like aluminium. Having brought in this nanowire mesh, we are not able to see it with the naked eye, but glass becomes effectively conducting, very, very low resistance associated with such glasses. And that's why the price difference is enormous compared to a commercial ITO and what we are able to produce in our semi-pilot plant. And this is the actual so-called factory. We call it a factory, but it's essentially R&D lab, semi-pilot plant, where we are able to produce day in, day out around 50 to 100 such pieces of glass, big size, 1 square feet kind of glasses. And these can be actually put to use. You can see lots of devices emerging from the lab. All of them are transparent type of futuristic technologies have been implemented using this kind of electrode system. And I just want to show you one or two results from Smart Window itself. Here is the case of using this metal mesh-based glass electrode in PDLC technology. You can see that the window is able to switch the color. Here is the live video of that. You can see the opaque state becoming transparent state with just application of the electricity. And you can actually take it to bigger sizes. Given the kind of sizes what we produce for the glass panes, we are able to actually build up a module of them, and we can actually turn on, turn off various glass panes at will. And this is yet another device. This is based on electrochromic principles. So you can see transparent glass getting into colorations based on the application of electric field between the two conducting glasses. And here is yet another example of microfluidic window, wherein we are able to pass liquid through glass panes and control now the transparency aspect. Now, electrochromic as well as microfluidic are being brought together. That's the ongoing project in the the time to thank my colleagues here, a bunch of them, co-workers and PhD students, and also co-workers from within India and also from abroad and from industry. I thank all of them, and also the funding agency, DST Nanomission, Indo-German project, and also SCRP Supra project. Thank you very much for your attention. Thank you.
Thank you, Professor Kulkarni. I invite Professor Suparna Mukherjee, Professor, Environmental Science and Engineering Department, Indian Institute of Technology, Bombay.
I'll be talking today on application of microbes and nanomaterials for treatment of water and wastewater. So recalcitrant organic compounds are often present in industrial wastewaters, and they are inherently difficult to treat. I will be talking about use of some novel microorganisms for treating such recalcitrant organic compounds. Nanomaterial-based processes also have a lot of potential for removal of pathogenic microbes and for removal of micropollutants such as pharmaceuticals and pesticides. And they are inherently very difficult to remove through conventional treatment processes. And even when present at a very low concentration, they are very toxic. We isolated some oil-degrading bacteria from contaminated soil and sediments using diesel as the sole source of carbon and energy. These two bacteria, Burkholderia cepacia and Exogobacteria morantiacum, were found to induce hydrophobic cell surfaces when grown in the presence of hydrocarbons or oils such as diesel. This was evident through bath assay results and also through the contact angle on a bacterial mat. So they developed higher water contact angle when they were grown on diesel or hydrocarbons. This made it evident that these organisms would attach onto the oil droplets and utilize oil from the oil-water interface. Later, we combined one of these organisms, Burkholderia cepacia, together with an algal consortium to degrade high-strength oily wastewater. The algal consortium was obtained from rock surfaces near Powai Lake, and this consortium was cultured in the lab and acclimatized to diesel. And after that, they were used to treat this high-strength oily wastewater in a three-stage rotating biological contactor as shown in the image here. These two cultures together could form a stable biofilm in the system. Burkholderia primarily degraded the oil. Algae could also use some of the oil mixotrophically. However, its primary function was to help in the immobilization of the bacterial culture. And it also provided stability to the system by generating alkalinity, because during oil degradation, pH drop was observed in the system when we tried using the bacteria alone. It also generated oxygen and thereby allowed using a much higher organic loading rate than we normally use in a RBC reactor. This was a three-stage RBC, and it gave very good performance when operated in a continuous flow-through mode at 21 hours HRT, and we could get good removal of oil from the oily wastewater. Of course, for coexistence of the two cultures, we had to optimize the nitrogen is to phosphorus ratio in the range of 28.5:1 to 38:1. Nutrient requirements were also found to be low. The system could be operated in a stable manner over the hydraulic retention time range 24 hours to 15 hours. Below that, excessive sloughing was observed. The biofilm in the first stage was predominantly bacteria with some algae, and in the second and third stage, there was more dominance of algae. And the first stage was primarily responsible for bulk of the oil removal, and the second and third stage primarily served as a polishing removal stages, as seen in the plot for TPH removal at various HRT. So the system could withstand the high organic loading and give good performance. However, here removal was due to both biological activity and sorption of the remaining oil that was not degraded on the biofilm. So primarily the aliphatic hydrocarbons in diesel, which is 80% of diesel, was getting degraded, and the remaining 20%, which is aromatic, was getting sorbed onto the biofilm. This is primarily because there is no aromatic degrading organism here. The Burkholderia was capable of degrading only the aliphatic hydrocarbons. You can see here by the third stage, there is no resolved peaks due to the aliphatic hydrocarbons anymore. This is the internal standard peak. And after more than a year, when the system was dismantled, there was quite a bit of oil sorbed onto the biofilm. So the part that is not getting degraded is remaining absorbed onto the biofilm. However, that oil does not have any of the aliphatic components. It is mostly the undegraded part that remains absorbed onto the biofilm. Now I'll talk regarding our work on disinfection of water using immobilized silver nanoparticles. So these are citrate capped nanoparticles prepared using the borohydride reduction method. And the size, mean size is 8.54 nanometers. And these nanoparticles were attached onto a amine functionalized glass surface, where the amine functionalization was done using APTMS through a series of steps. And this provided good attachment of the silver nanoparticles to the glass substrate. And the loading was 3.26 microgram per centimeter square. Subsequently, this glass substrate was 1 centimeter square of this glass substrate was dipped in 100 ml of water under static condition, and 10 to the power 3 CFU per ml of E. coli was disinfected in the system. As you can see, complete disinfection could be achieved within 50 minutes. And this system could be reused multiple times. And the leaching was also studied. Silver leaching into water never exceeded 25 ppb. However, there was some removal of silver during the multiple cycles of reuse from the surface. Now I'm showing a comparison of performance of this AGNP glass with that of colloidal silver nanoparticles of the same mass and of the same size. You see that the colloidal silver nanoparticles are less effective than the AGNP glass substrate. This is primarily because the colloidal nanoparticles get internalized within the microbial cells. As a result, they are not available to the other microbial cells, and these nanoparticles aggregate over time and they lose their efficacy. When we look at the surface of the microorganisms in PEGSIM, we see that for the AGNP glass, there is no silver on the surface. But there is silver on the surface for those treated with the colloidal nanoparticles. So the mechanism of the two systems seems to be different. So then we used a silver plate of same size and a silver plate with a layer of AgCl on its surface, so a chloridized silver plate, and compared it to the AGNP coated glass plate. So what we find is here also, the AGNP glass substrate provides a better disinfection than the silver plate or the chloridized silver plate. And the release of ions is much more from the silver plate and the chloridized silver plate. But the action of the AGNP glass is with lower silver release is better. This implies that its mechanism of action is different. It does not act through the release of ions, or does not act solely through the release of ions, but also has direct contact mode of disinfection. As a result, we find that it is more robust to changes in water quality variations, such as alkalinity, hardness, and natural organic matter. So the system with the AGNP glass substrate was more robust to higher gnome concentrations and could give disinfection even at higher gnome concentration compared to the chloridized glass surface. Now I'll talk about photocatalysis using TiO2-ZnO nanocomposite, which was synthesized using a sol gel route. Here we looked at the impact of varying the Zn to Ti ratio from 0.1:1 to 1:1. And as we did that, we saw changes in morphology of the nanoparticles such that at 0.1:1, TiO2 was present in the form of anatase. As we increased the ratio, we saw presence of butyl together with anatase. At 0.3:1, we found presence of the mixed oxide phases, that is ZnTiO3 and the Zn2TiO4 together with anatase and butyl and butyl. And this gave to a better band gap lowering. In fact, it gave to a band gap of 2.4 electron volts compared to TiO2 alone, which is 3.2. All these nanocomposites had an effect of band alignment, which lowered the band gap such that they were visible light active, as is shown by the decolorization of methyl orange, all of these could be decolorized, could decolorize methyl orange using visible light. Subsequently, we show that this nanocomposite could be used to treat 17-beta estradiol. So here, low concentration of the nanocomposite was used, only 10 milligram per liter of the nanocomposite. Together, that is the S3 and the S4 nanocomposite with a ratio of 0.3:1 and 0.4:1. And we see the best performance with S3 with UV irradiation, and S3 with visible irradiation was slightly less than that. However, S3 performance was always better than that of S4 in terms of the rate and extent of removal of 17-beta estradiol. And along with transformation, we also saw that significant mineralization was also happening, which was evaluated through TOC removal. Subsequently, we also looked at the reusability of this nanocomposite, and it could be reused multiple times with an intermediate calcination step for calcination for about an hour. And while it was getting transformed, 17-beta estradiol formed products during photocatalysis that were no longer estrogenic, because we used the E-screen assay to look at estrogenicity changes. And over time, the 17-beta estradiol was transformed to intermediates that were not estrogenic, and quite a bit of it was also mineralized. However, when only photolysis was used in absence of any nanocomposite, we found that there were intermediates formed that were estrogenic in nature. So the estrogenic activity was not removed through photolysis alone. In conclusion, there is much scope in developing microbial processes for treatment of recalcitrant industrial wastewaters, and there is a need to explore nanomaterials for water treatment applications in areas where conventional processes do not work effectively. However, the effect of co-contaminants in water needs to be evaluated, and during use in water treatment, the nanomaterials needs to be immobilized for effective treatment, and the ion leaching needs to be minimized also. So these are the concerns to be kept in mind when developing nanomaterial-based processes. With that, I'd like to end by acknowledging my students whose work I presented, and my collaborators and the funding agencies. Thank you.
Thank you, Professor Mukherjee. I invite Professor Rohit Srivastava, Professor and Head of Department of BSBE, IIT Bombay.
A very good morning to all of you. My name is Rohit Srivastava, and I wish to thank INAE for bestowing the fellowship to me this year. Let me start my presentation. So if you can see the screen now, I'll start from slide 1. So our lab in the Department of Biosciences Bioengineering is called the NanoBios Lab, and we do a lot of translational research, which is why I have titled this Affordable Healthcare Technologies, and I'll give brief glimpses of what is happening in our lab. So our lab is part of the Department of Biosciences Bioengineering at IIT Bombay, and we have about 29 faculty, several PhD students and master students working in the department. All of these students contribute to the excellent publications and patents being filed from the lab. So if I start off with the healthcare challenges, many of you know this data, but let me just highlight one point, and that is on the right side of your screen. The data shows that India spends very little on health expenditure per person. Of that, 70% is private spending and only 30% is public spending, which means that every one of us, whoever, wherever is working on translational research has to keep one thing in mind, and that is affordability. And this is the biggest solution that one can provide to this country. So the solution is that we can make affordable point of care devices, affordable technologies, affordable therapies, whatever. But they have to be able to have simple reagent preparation, simple storage conditions, simple training, and everything should be easily available to everybody. With that in mind, our lab works on several different domains. We are part of bioengineering in the department, which means that we have several verticals to work under. So we work in therapy, which is nano-based drug delivery, nano-based cancer therapy, nano-based orthopedic materials, and many such things under nano. We also work on diagnostics and devices. So we work on the paper-based diagnostic devices. We work on solution-based assays. We work on paper-based assays, all of them being integrated with readers. And we also work on several MEMS devices as well. So we have micro needles and micro pumps that we are also working on. Many exciting things happening in the lab. We have also entered many new areas, with the advent of COVID. And as you can see, we are now moving into IoT-based health solutions, protective equipment, COVID care research products, disinfectants, sterilization products. We are also moving into chemotherapy-induced alopecia. We are also having a project now on forensic diagnostics. So many important areas, and all of the areas that you see under bioengineering being covered in one lab. I'll show you how. So if you look at this slide shows the essence of what happens in our lab. We've got several products out there in the market. We've got many products under clinical validation, which will hit the market very soon. And this happens not because our lab does all the commercialization, but because we have students who have set up companies. Now, these are the companies that you see in this slide: Dynasense, Mozen, CareAnnex, Neodox, Nordetect, Biosense Technologies, and so on and so forth. So more than, I think, 10 students have set up companies. There are many that we are setting up as I currently speak, and many more that are in the pipeline. And this happens because there is this team of students with me who are passionate about taking technologies to market. Now, the most important technologies that hit the market are these three that you see on this slide. There was a student who worked with me in 2010, I think 9 to 11, Abhishek Sen, who had set up his company Biosense Technologies Private Limited. He came out with several products that went through the lab, through several projects that we did in the lab, and finally hit the market. The most successful one is the one in the center, which is called Group-2. And this is a mobile-based urine analysis system, and it has its own indigenous strips as well as a reader. And the reader is a mobile-based reader. This was way back in 2010-11 when mobile phone was not used for diagnostics. This was the first case of diagnostics being shown on mobile phone. And from then on, this became a hot market for India. We also worked on our own indigenous glucometer, the one that you see on the right side of your screen, which also hit the market. And it was the most affordable glucometer and strips to have come in the Indian market. The one on the left side was the one that Biosense put in the market for non-invasive hemoglobin monitoring. That also became a big commercial success. So if you look at several things that happened in our lab, there are many other things. We went through several such projects with Biosense Technologies. We went and did a smart sense device, which was point of care device for critical care analytes. We also did a Uritsa device, which is just for albumin and creatinine. And we also did a small device, which was called Electrofinder, that could do sodium and potassium at bedside. So many such products came out from the lab, and they have all been clinically validated. Many important things that have happened in the lab started out with this first example that you see in the screen, which was UCheck. And UCheck happened because the student and I were passionate about taking an idea all the way from lab to market. And again, let me remind you, this was in 2009 when translation was just a keyword. And we were the first people in those times to show that something from the healthcare domain could actually go all the way from an idea to commercialization in about 18 months and create a market for itself. UCheck was one such example. We did a lot of survey, figured out what the problem was in these path labs that we surveyed, figured out what solution we could put to them, and came out with our own solution, which is what you see on the screen. And this is a image-based CCD array sensor using a mobile phone. And this mobile phone could just take images of the strip that you see at the base and take images one after the other at time points, which would then determine the end point of that color reaction on the strip. And finally, we could tell you exact values of the analyte that we were trying to detect. And if you look at analytes, these were the analytes, the 10 parameter urine dipsticks. There was also a 10 plus 2 parameter, which was including albumin and creatinine. And when you compare it to what the market was, we were at least 1/3, to 1/5 cheaper than what was already existing in the market. Plus, we did not have a bulky reader with it. We were just using a mobile phone. So that became a big commercial success. We went on to our second product, which was Suchek. And at that point, ICMR invited several people in this country to come and work on an indigenous glucometer project. When we started working on this, again, we looked up what the background was. So most importantly, you have to do a clinical study. You have to figure out where the gaps are. You have to do a patent search to figure out where somebody can hit you with a patent infringement. And then you have to actually start working on a project. So never ever start a project, do a project, and then go back 1 or 2 steps. Always start from finding the problem and then go ahead to find a solution. So when you do that, we figured out what the blood glucose monitoring could lead to. Of course, the chemistry is known to all of us. The chemistry cannot be protected. It is a known chemistry, and everybody uses it. So we were free to use it. The only thing that we made a difference in this was using color pads, and using ratiometric sensing, so that we could give you correct values. And we came out with our own strip. We came out with our own reader, and also did a Clark's error grid analysis of these strips, and figured out that more than 95% of the results were within zone A of the Clark's error grid, which meant that this device could pass all the tests and go on to be commercialized. This was possible because then it went through all the approval process, finally got approved, and got released in the market. It actually made a big impact in this country because at that point, ICMR had given us a target of 2 rupees per strip. Of course, we couldn't meet that target, but we were able to do 5 rupees per strip. And we priced each one of these 50 strip bottles at 250 rupees. They had manufacturing capability of a large number of strips per year. And there were several features with this glucometer that we then had to make sure that all of these features could be integrated in the newer version as well. So there were many things happening in that time in the lab. We also started working on a Wellcome Trust funded project, for which we won a big prize from HIT Labs, New York, USA. And we were asked, we were fortunate enough to submit this project to Wellcome Trust UK under their Affordable Healthcare in India scheme. Under this scheme, we were asked to come to London and present the proposal. So we presented the proposal, we presented the concept that we had in mind, our solution to the problem, and we were funded by Wellcome Trust to see how we could actually take this project forward. So what you see here is our end goal for the project, where we actually proposed to them a point of care monitoring for critical care analytes. And this included sodium, potassium, glucose, pH, chloride, and urea. So many of these that we did, that were finally able to validate with samples that we received from KEM Hospital. We had an ethics committee approval from there, and from there we were able to do all the clinical validation and show that the data was robust enough to be transferred to the company, and we finally transferred it out to Biosense Technologies. So the business model was, we were making it in cuvettes, and the cuvettes is what we were selling, and we were not worried about the reader, which was actually a really cheap reader that we had made for this. Went on to make many such versions. We also worked on an albumin creatinine ratio sensor, as you can see here, using ratiometrics, again color strips, and the reader which was made. And then there was a lot of data that we generated from hospitals, which proved the robustness of the data. Also worked on microneedles, as you can see in this slide. I'm just giving you a brief overview of what happens in our lab, so that you also understand that there is tremendous potential for all such projects in a bioengineering lab that have potential to reach the market. Microneedles is a terrific area because there's a lot of emphasis now on delivering vaccines, and if we can make these microneedles stable with the drug, with the vaccine, then there is a lot of potential for creating a chain, a supply chain for these vaccine delivery. So we have worked on silicon microneedles, we have worked on polymer microneedles, and both have been big success stories, as you can see from our lab. And we have actually shown delivery of model drugs from these microneedles. We are also working with another company to take this forward. There was a concept in our lab in those times where we showed that you could put these microneedle patches on the backside of a smart device and make sure that on the press of a button, an amount of drug went into the skin. So this concept caught on really well. One PhD student started working on the idea, and we were able to show a lot of data around this. We prepared the microneedles in IIT Bombay, micromanufacturing facility. We actually went on to compare these microneedles with what existed in the market for drug delivery. We went on to make our own smart device, went on to attach the microneedle to the smart device along with a micropump, and then showed that we could actually deliver drug. So the final prototype went through a lot of iterations. These were the iterations that we went through, where we showed that these microneedles were able to deliver drug. As you can see in this figure here, on the press of a button, you could actually modulate the release of drug, and you could do a drug release in any pattern that you wanted. So this again has a lot of promise for the future. Many other things we are working on. BIRAC, I've been associated with BIRAC for last 10, 12 years now, and in most of their panels, as expert member. But what I have learned sitting there is that there is a terrific ecosystem now in this country. All started by Dr. Bhan when he was there in DBT, and then later continued by Dr. Renu Swarup, who actually made sure that there were a lot of these schemes that could be brought forward to take academic research into commercialization. There's one such scheme in BIRAC, which is academic innovation research, through which they fund academic research and make sure that it goes all the way from TRL1 to TRL9. This was one example where we pitched for a project under BIRAC and wanted to do a total cholesterol, HDL, LDL, and triglyceride monitoring in strip format and in liquid assay format. And we pitched for a project under AIR scheme and got it funded. Went on to show all the data under the AIR scheme, as you can see here, made a device for it, made different versions of the reader, made sure that we tested it in a hospital setup, and made sure that the data was robust enough to be taken back to BIRAC for a contract research scheme, which is the second phase of this project, which takes it all the way from TRL4 or 5 to TRL9, which is commercialization. So a lot of exciting stuff happening in our lab, as you can see on this one slide that shows you many, many things. I have not covered many things. We are also doing glycated albumin sensing using a reader. We are making a mobile reader for doing lateral flow assay reading. And we are working on several of these lateral flow assays in our lab, including T3, T4 TSH, troponin INT, vitamin D3, glycated hemoglobin. So many, many, many things that are happening in our lab. And all of these are adding value to the country's ecosystem because many of these have potential to move forward in either a startup or technology transfer, which can benefit this country. We also work on many nano-based technologies, as you can see from this slide. We are setting up companies around our photothermal therapy project, setting up company around our bone fixation screw or biodegradable screw project. We are also setting up a company around our nano-engineered sponges to fight periprosthetic infections. So many, many things happening, and there is a lot of potential to take all of this to the market. We also do a lot of social innovation with all the stuff that we've done in our lab. We want to bring them under one umbrella and do malnutrition screening and anemia screening in this country. We've actually got a center of excellence funded by DBT, which gives us now the scope to look at screening of children and women in Maharashtra as well as in 2 states in Northeast. So using all these products that you see on this screen, we'll be able to do, and all these products are from my student companies. Many of these products are selling very well in the market, and now they have potential to scale up as well. With data that we provide to the government, we hope that it will actually help the government tackle the problem of malnutrition as well as anemia. So many things that you see. We also have a student who set up Care Annex Technologies, and he's got a product Care Mother, which can do tracking of pregnancies from 0 to 9 months and can actually give you data that can detect high-risk pregnancies and can actually refer them to a tertiary hospital or a secondary hospital so that they can be taken care of. He's already saved a lot of lives in this process. We do a lot of screening, as you can see in this slide, in different places in Rajasthan, in Ahmednagar district in Maharashtra. A lot of these devices have been used in screening purposes in northeast corners of India, in slums in Mumbai, and many places that have created a big impact. I'll just go through some of this data, and we make sure that we showcase our work to the government. The Honorable Prime Minister has visited IIT Bombay and was very appreciative of technologies being worked in our lab as well as other labs in IIT Bombay. And there were many things that we've actually received big awards for. But this is all due to work of students, and we hope that the students keep working hard and harder so that we can earn more laurels for our country. We make sure that we present our work at several places. We always do workshops. We always do exhibitions so that we can teach students what is happening in our lab. We always give internship to students so that we make sure that others are also able to use the facilities of IIT Bombay and learn from what we can actually show them. We have a big partner network, different IITs, different institutes, hospitals, several startup companies, incubators, industries, and a very large lab. At some point, I had more than 50 members in my lab, and we used to run it like a company because we wanted to make sure that more and more products were being worked in the lab and more patents were being filed. So if you look at output from our lab, not just products and patents, we've got students who have graduated from the lab. 35 PhDs have already graduated in 15 years of me being at IIT. More than 20 PhDs are registered with me. Many publications, more than 200 publications in high impact journals with an H index of 37 now from my lab. Many project staffs and interns trained. Most importantly, number of patents filed. So we filed more than 125 patents now. 25 of them have been granted, and many are in the final stages of review. And I think the biggest thing that we have contributed is we have actually added to the high value jobs that we have created, the patients that we have benefited. And I'm very thankful to all my students who worked so hard to make sure that all these products have seen the market, have actually been launched in the market and have created an impact in the market, have benefited the patients. With that, let me also show some of the funding that we've received from most of the top funding agencies in India, and we've been able to showcase many of these things at several places. Let me end this by expressing my deepest gratitude to my mentors, Professor G. Padmanabhan, who chairs the BIRAC committee, chairs several committees in this country. But he's been a mentor to all of us, all the youngsters in this country. He's shown the way that innovation is the key word. If we can keep working on innovation, there is no end. We can keep working all our lives, as he still does, and he still heads all these countries. Dr. Renu Swarup, who is an idol to all of us. The way she has brought BIRAC and DBT to the forefront is phenomenal. And my biggest mentor, Dr. Mrs. Manju Sharma, who's always appreciated the hard work that youngsters do for their country and keeps encouraging us to do more. Let me thank all of you, all the faculty members who have collaborated with all my students, all the startups, and all my mentors across the country who've helped our lab reach where it has. Thank you very much. So thank you so much.
Thank you, Professor Srivastava. I invite Professor Sandeep Verma, Secretary, Science and Engineering Research Board, New Delhi.
As part of new fellow induction in INA, I'm going to tell you a bit about my research that is being conducted at Indian Institute of Technology, Kanpur. We primarily work in 3 different areas. One which relates to chemical neuroscience, where we engineer structures that are able to deliver neurotransmitters, more particularly gaseous neurotransmitters inside the neurons. Second part of our work, which is related to structured surfaces, is being conducted where we look at morphologies that can generate colors, and that has very interesting potential applications. I'm going to talk to you about that a bit later. And the third aspect of our work is related to green batteries, where we use nucleic acid fragments to generate battery and capacitive properties in given materials, which are totally biodegradable. Thus, they have enormous potential to be taken further for electronic applications. Let me start with chemical neuroscience, where we are working with the aspects of making neurons more active by the help of indigenously designed compounds that are able to deliver gaseous molecules inside the neuronal cells. So just to show you an example, on the left side of the panel, I have a structure for your consideration where the blue oval represent the features that would allow this molecule to assemble in a given fashion. And the brown oval is going to eventually release nitric oxide, which all of us know is a small molecular gaseous molecule, but it is a very important gaseous neurotransmitter in our body. And a lot of our biological mechanisms and pathways relate to the generation of nitric oxide and its post-synthetic effects. So what I'm showing you as part of the trace that is on the left side of the bottom panel is amount of nitric oxide that is being generated within a given neuronal body. And as you can see very clearly, that around 28 hours to 30 hours of administration of this particular molecule in neuroblastoma cells, we are able to generate nitric oxide at the highest amount of fluorescence that is achieved within the neuronal body. That tells us that this molecule has the potential to deliver a gas inside a neuron. On the right-hand side panel, the two rows at the top tell you where we have used phosphate buffer saline. So it's a control experiment where we are treating just salt water or just the salt water is given to our neurons, to the Neuro-2A cell line. As you can see, nothing much is happening within day 1 or after day 2, right? But if you look at the bottom two panels, where we have added our compound that has the ability to deliver nitric oxide, you can easily see that after day 1 and after day 2, there are growth of hair-like structures from the neuronal body that tells us that nitric oxide is going inside the neurons, and it is developing through protein expression, overexpression, if you will, the kind of hair-like structures that are coming out of the neuronal body. And that tells us that interference is indeed happening because of our molecule, because of this engineered structure that has the ability to deliver the neurotransmitter gas, which is nitric oxide. So here is a zoomed out image. And as you can see, for control for day 1 and day 2, it is very different from day 1 and day 2 when we have added our compound. And that tells us that a lot of interesting application in neuronal regeneration, in neuronal engineering can be envisaged by these molecules. And we are now at the stage that many of these molecules are being taken inside the animal cells to deliver nitric oxide gas within an animal or in vivo systems. Let me move ahead and tell you about another topic of our work, which is applied coloration. And in this particular aspect, what we are working on structural colors, such as the variety of very beautiful, vibrant and fluorescent colors of butterflies, of peacock feathers, and so on and so forth, where colloidal assembly of polymeric and silica spheres and many of these photonic based systems are used by biological systems to generate color. So these are very complicated, complex topologies, which when the light is incident on them is able to generate color. So what we envisage, that is it possible for us to come up with synthetic molecules from the biological realm, and can we redecorate surfaces to create structures which have periodicity, and if light is incident on them, are we able to generate colors in a varied color palette that could come out of interaction of light with these materials? So this particular slide shows the molecules that we have used to put on the surface. And if you will, you can look at the scanning electron microscope images, microscopy images that shows you these oval morphologies which are being decorated on the surface. And we have done quite a number of studies based on focused ion beam interaction with these molecules to study their ability. And we were able to now take this structured surface for study by putting light incident on these surfaces. And what we were very amazed to see is that when you dry out these molecules on surface, you get non-ordered spheres within a larger area, which are within the larger area of the of surface where we have spread out our molecule. And eventually, by the help of Mie scattering phenomenon, we were able to incident light and generate colors and through a colored palette, which is shown in the next slide. So film topology is shown in the palette in the panel D. And if you incident light, the bright field images of these peptide films, which are put on a given surface, shows you a uniform coloration. And we were able to not only put it on a surface, but looking at both transmission and reflectance of these spheres, we were able to paint the surface in a very large scale or sort of large area painting, where we had written the letters IITK for IIT Kanpur and TAEU for Tel Aviv University, where it was a Indo-Israel joint project. And what you can easily see is that colors were indeed generated because of these spheres, and we were able to generate a total color palette, and which is shown in this particular panel, in the rightmost panel, where the chromaticity diagram shows you the kind of colors were possible from these spherical structures or oval-like structures which were deposited on the surface. We have also worked on stem cell engineering, where we look at these very fundamental stem cells which are coming out of bone marrow cells or umbilical cords, where we take umbilical cords with due human consideration. We use the kind of ethical judgments to be applied for such type of harvesting. We harvest the stem cells, and we look particularly at the proliferation of these stem cells, where we would like to multiply these cells under a definite small molecule, which is called a small molecule engineering of stem cells. So what we have done here is we have primarily looked at stem cell biomechanics, whether stem cells, when we have applied our compound, the fluidity of these stem cells get modified. And what we have done is that we have put these stem cells on a given surface, look at the atomic force microscopy through the AFM indentation studies, where we have looked at the Young's modulus of these stem cells before and after application of our molecules. So membrane fluidity of stem cells, once you are challenging them with a small molecule, directly correlates to their proliferation. I won't go into the detail, but soft cantilevers were used, and stress strain relaxation profiles were generated with the help of AFM indentation. And finally, a mathematical expression was used to determine the force constant of this property of getting more fluidity in stem cell membrane through the Hertz model, which was used. And this paper again is already published and available in literature. The force mapping of peptide treated human mesenchymal stem cells is shown in this particular slide, where we have taken recorded the force maps of the human mesenchymal stem cells as a control, where no molecule was applied. And we have then taken 3 different measurements at different time intervals, if you will, from the peptides, from the organic molecules that we have created for stem cell engineering. And I'm very excited to report to you that we found a 2.5-fold increase in the Young's modulus in the fluidity of these stem cells once they were challenged with a given peptide, as it is shown here. So with respect to the control that you can see in the trace, the human mesenchymal cells, either when treated with compound number 1 or compound number 2, I'm not showing you the structures at this moment, we were able to see increase in the Young's modulus. And that already told us that our compound is not only going inside these stem cells, but it is changing the fluidity of these stem cells, which is directly relevant or related to the proliferation processes that we are going to study. So now the question is, once you have these Young's modulus in your hand, which is in your favor, what kind of experiment one can design for stem cell engineering for proliferation in particular? And that experiment is what we call as the wound formation in the suspended cultures of stem cells. So if you can go from left to right, what I'm showing you here is that if you take a petri dish, you inoculate it with a low density of your human mesenchymal stem cells and create an artificial insert, or put a artificial insert that could be treated as a wound inducing insert, and then you let this whole stem cells culture for about 24 to 48 hours. After this time interval, if you were to remove the insert, what you would find, and very interestingly so, that there would be a gap in your culture, which would be visible under a microscope, where you would find that the insert did not permit the cells to grow in that given area. But if you let it proliferate for a while, the view that you see under a microscope would get totally diffused, and the proliferation would occur as cells would migrate from one end to the other to close the gap from both sides, right? So it's a very small but very compelling experiment that we have performed, and the results are shown here. What I am showing you as part of result is that if you look at panel A and the yellow broken line, it tells you that stem cells are on both sides, and there is a gap which is being treated as a gap because it has been caused by the wound inducing insert, right? Now we have applied the two compounds I was referring to in the previous slide when we were looking at the AFM indentation study. What we let them do is that under control experiment or under the influence of these two molecules, we let the stem cells grow. And I'm very happy to share with you that one of these compounds actually accelerated the proliferation of these mesenchymal stem cells. That tells us that synthetically we can have control over stem cell engineering. So not only for proliferation, for regeneration, but we can also use it to create specialized cells. So for example, from stem cells, you can go to fat cells, you can make other cells of a very special lineage. So that control, if one were to have over stem cells, that is the real regenerative engineering or regenerative engineering of these very fundamental cells that are stem cells. So we are on the track. We now have a couple of very exciting experiments underway, including the one in animal models, where we would like to see if we are able to grow, say, a new pancreas-like cells or new heart-like cells. So that is going to be very exciting for us. So finally, I just tell you a bit about what else we do. We work on bioanalytical detection. We work on new antibiotics. We work on neurodegeneration and neuroregeneration. A lot of papers, I'm not going through the detail, are presented here. We also work on conducting materials, which I talked to you about, the capacitive property of nucleic acid-based batteries, interfacial systems, and computational modeling of many of these systems that we study experimentally. So finally, I would like to thank my current co-workers, a group of very talented students, so about 10, 12 PhD students, and about 7 postdocs who are working with me, including my very valued collaborators who work across disciplines and across institutions and abroad. And finally, the talk will not be over if I were not to thank the funding partners from Department of Biotechnology, DST Nanomission, SCRB. So all these funding partners, and I've not put ICMR. We just received something very special, a project from ICMR on an antibiotic and multi-drug resistance. So all this in a nutshell tells us, or sort of I would like to present to you what we work, but I hope I'll get another opportunity sometime soon to tell more details about our research. Thank you very much, INE, for the fellowship. I would like to thank the president and the council members of INE for this very significant honor. Thanks for listening. Thank you very much.
Thank you, Professor Verma. I invite Dr. Ajit Kumar Mohanty, Director, Bhabha Atomic Research Center, Mumbai.
Respected Chairman of this special session and Fellows of INAE, ladies and gentlemen. Thank you very much for giving me this opportunity to present a part of my work. Here I will be talking about the probing of early universe using accelerators. Presently, I will be telling my involvements in 2 major collider-based international collaborative experiments, Engg, which stands for pioneering high-energy nuclear ion experiment using relativistic heavy ion collider at Brookhaven National Laboratory, USA, and central mule solenoid using Large Hadron Collider at CERN, Geneva, that detected quark-gluon plasma, a new state of matter in which our early universe would have existed a few microseconds after the Big Bang. These experiments create a mini universe in the laboratory by colliding two oppositely moving heavy ions like gold ion at RIC or lead ion at LHC, moving nearly relativistic speed using state-of-the-art accelerators and detector technologies. Let me define what we mean by quark-gluon plasma. As you all know, that the matter that makes up our visible universe is made up of atoms which consists of a nucleus with orbiting electrons. Nucleus contains protons and neutrons that are composed of quarks. Quarks are confined within proton or neutron by gluonic attractive force. The picture below shows how the atom looks, and inside the atom there is nucleus, and inside the nucleus there are protons and neutrons, and inside the protons and neutrons there are quarks. And it is believed that our early universe, few microseconds after the Big Bang, would have existed in the state of these quarks and gluons. The next slide shows a pictorial representation which shows a tiny point which is basically a Big Bang, and later on, after the Big Bang, the universe expanded and cooled at about 10 to the power minus 4 seconds, that is 1 microsecond. The universe consisted of soup of quarks and gluons, electrons and neutrinos. When the temperature of the universe decreases to 10 to the 12 degree Kelvin, this quark-gluon soup collapsed into protons and neutrons and deuteriums. And as the system expanded, then more atoms, there was hydrogen-helium fusion, and they formed the atoms, and from the atoms there are galaxies, stars, and when there was a supernova explosion, finally many small units, including our Earth, was created. Today, what we see as Earth is a low temperature, about 3 degree Kelvin, and we believe it would have created after 1 billion years ago. But what I will be talking here, that after the Big Bang, the next circle shows it is the state where the universe is supposed to be composed of quarks and gluons at a temperature 10 to the 12 degree Kelvin and after 1 microsecond. And this probably we cannot study universe because it has been created, but we can create in the laboratory. For example, if I take two heavy ions, either gold or lead, when they move with a relativistic energy and collide, this is what happened. They collide and then a quark-gluon plasma is created and they expanded. This is the scenario which we can create using an accelerators. So my talk therefore will be concentrating on two relativistic colliders. One, both are heavy ion colliders. One is located at Brookhaven National Laboratory, USA, and another is the Large Hadron Collider, LHC, at CERN, Switzerland. There are two independent rings which circulate heavy ions like gold or lead in opposite directions and are made to collide at designated experimental setup. These are international collaborative experiments involving many countries, and India is also a party to these experiments. First, let me concentrate on relativistic heavy ion collider at Brookhaven. Fascinating facts about this machine is it is a tunnel underground 3.66 meter below the ground. Its circumference is 3.84 kilometer. In the gold beam, it is accelerated to move almost the velocity of light, that is 99.995% velocity of light. It has 1740 superconducting niobium titanium magnets, thousands of particles produced per collision, and that point, at the collision point, the temperature of that tiny system is 10 to the power 12 degree Kelvin. I recall here, the center of the sun, the temperature is 10 to the power 7 degree Kelvin. So it is 10 to the power 5 times higher than what the core temperature of sun. This is how pictorially the reactor, the collider looks like. It has several components. Like first, it is a linear accelerator where the heavy ion starts with energy few MeV per nucleon. Later on, it passes through stages of accelerators like booster synchrotron, alternate gradient synchrotron, and finally it went into a collider, storage rings, where the energy finally it attains 100 MeV per nucleon. And inside the storage ring, they are made to collide, and there are 4 experimental points. One is called Phoenix, Phobos, Brahmos, and Star. Indian community, particularly BRC, participate in this Phoenix experiment. And this Phoenix detector, Phoenix, it stands for Pioneering High Energy Nuclear Ion Experiment, and it is a mega scale detector having several types of detector. You can see a small person standing there, and with respect to this person, this is the size of the detector. It is about 6 to 10 times taller than a normal human beings, and it has many detector components like dip chambers, ped chambers, time of flight detectors, electromagnetic detectors, muon tracking calorimeters. And in India, particularly BRC, we design and participate in this muon tracking chambers. This is how the muon tracking chamber looks for. Here, our contribution has been, we participated in the simulation and reconstruction software. We participated in the fabrication of muon tracking stations at BRC, and obviously also participate in the physics analysis. More explicitly, we developed PISA, a Phoenix integrated simulation application, development of tracking of particles using artificial neural network and principal component analysis based pattern recognition, multi-level trigger algorithms, hardware and software optimization, and finally sophisticated physics analysis. And this is one such PISA, a solely important simulation tool for this Phoenix experiment, and BRC and Vanderbilt University USA were solely responsible for this development. Another accelerator who participated in this experiment is the Large Hadron Collider at CERN, which you all know because this is the accelerator where 2 protons they move in opposite directions and collide. The primary motivation of this experiment has been to collide the protons to create a Higgs boson, popularly what you all know as the God particle. But however, there is also another program to collide lead ion moving opposite directions to create what I call this quark-gluon plasma or the mini universe. In this experiment, Large Hadron Collider, India has strong contributions like RRCAT, Rajaramana Center of Advanced Technology, and Bhabha Atomic Research Center have contributed significantly in grid computing and supplying various components of the Large Hadron Collider accelerator. The items that were mass manufactured in India and delivered included precision motion positioning system, PMPS jacks, superconducting corrector magnets, heater discharge power supplies, local protection units, etc. to name a few. And in Large Hadron Colliders, there are several experimental programs. India, where it participated in 2 major collaborations. One is CMS, which stands for Central Muir Solenoid, and another is ALICE. And in BRC and many other universities, we participated in this CMS experiment. And bottom one shows the typical experiment, and left hand side it is the 5-storied building, and middle one is the detector. You can make out the dimension of the detectors. And in this program, BRC, TIFR, and many other universities, Shah Institute of Nuclear Physics, IITs involved. And at some point of time, I was also coordinating this experiment as a spokesperson as part of India CMS collaborations. BRC involvement, particularly in this experiment, has been quite significant. As I mentioned, although the Higgs search using proton beam was one of the primary motivation of this CMS experiment, it also records the data when 2 heavy lead ion collide at relativistic energy. This process creates a soup of quark-gluon plasma, QGP, which mimics the formation of early universe. The BRC group was strongly involved in the study of QGP using CMS detector. BRC group has participated in 2 major detector systems, the pre-shower silicon strip detectors and gas-based resistive plate chambers detectors. When it comes to silicon strip detectors, the silicon sensors made for the pre-shower detector are first of its kind to be developed in India with active participation of BRC and then given to Indian industry like Bharat Electronics Limited at Bangalore for large-scale production. BRC supplied about 1500 numbers of large area 32-strip silicon strip detectors. Developing silicon detectors with very stringent electrical specifications and uniformity over a large area of 40 centimeters square was a challenging task. Such technology did not exist in our country. In view of expected radiation damage, the technology development was targeted to produce detectors with high breakdown voltage and low leakage currents for ensuring 10 years of operation without failure in the high neutron and gamma radiation environment of LSC. And this is how the pre-shower silicon sensor looks. It is the 32-strip silicon sensor made up of 4-inch wafers developed by BRC, and the bottom one shows the front-end electronics developed by SAP. Both are integrated, and the right-hand side it was all mounted. This is part of the CMS detector, and pre-shower comes at the end close to the beam pipe, and this is where the silicon strip detectors of BRC is located, sits there. Another area which is participating in the detector is resistive plate chamber detectors, RPC. BRC has also taken part in making resistive plate chambers, a new type of large area gas detector, which are crucial to signal the passage of a muon through the CMS detector. The Nuclear Physics Division of BRC and Punjab University Chandigarh jointly have built, assembled and characterized about 70 resistive plate chambers for the CMS upgrade along with copper cooling systems. Few slides below it shows how a typical resistive plate chamber looks. The left side is the assembly of RPC, that NPD, BRC. Right hand side shows fully integrated RPC with gas gaps, front-end board, electronics board, copper cooling and high voltage connectors. This shows the copper cooling cells fabricated at BRC for all the RPCs used in CMS. And this is finally where the RPC is stationed in the CMS detectors. Okay, finally now I will come what results we have got out of these two big experiments. I will mention here the relativistic heavy ion collider, which was at Brookhaven, that is world's first heavy ion accelerator. It started its collision sometimes in the year 2000, and major results started coming from 2001 onwards, and the full gold run was completed in 2002. Later on, deuterium and gold control experiment was carried out in 2003. And in 2003, there was a press release. It says the latest result from the relativistic heavy ion collider, the world's most powerful facility for nuclear physics research, strengthens scientists' confidence that weak collisions of gold ion has created unusual conditions, and that they are now on the right path to discover a form of matter called the quark-gluon plasma, believed to have existed in the first microseconds after the birth of the universe. And later on, these experiments were confirmed, and all the results were published in several important journals, including Physical Review letters, and there are much more letters and experimental papers which are highly cited. And this is the story of the experiment that was carried out in relativistic heavy ion collider. Later on, after a decade or so, the CERN experiment started. CMS, ALICE, they are the experiments which also carried out heavy ion collisions, creating the quark-gluon plasma, the so-called mini-universe. So I will not go further. I will just summarize here, telling that subsequent experiments using relativistic heavy ion collider at Brookhaven National Laboratory and Large Hadron Collider at CERN on many aspects of the heavy ion collisions, including the measurement of flow velocity, viscosity, jet quenching, etc., to name a few, have proven beyond doubt that the heavy ion collisions at high energy create a new state of matter comprising of quarks and gluons of extreme temperature and density, a state mimicking the conditions of early universe of a few microseconds after the Big Bang. This is an important science discovery describing how the normal nuclear matter undergoes a phase transition to a deconfined state of quarks and gluons under extreme temperature and pressure. On the other hand, this observation has been possible due to the use of fast of bit kind accelerators, relativistic colliders, state-of-the-art detector systems, including high precision engineering modules, cryogenics, superconducting magnets, and of course finally the physics analysis. I think I'll stop here. Thank you and Jai Hind.
Thank you, Dr. Mohanty. Ladies and gentlemen, thank you and Jai Hind.